Hello everybody and welcome to the vectors unit, and here's the cartoon character Vector with his squid gun, oh yeah, and some vectors, mathematical vectors, to do with what's going on here. So a vector is a quantity that has both magnitude and direction. The magnitude is what we call the size of the vector. And compare that with a scalar that has magnitude only. So distance and speed are scalars, displacement and velocity are vectors. Temperature is a good example of a scalar. It doesn't make any sense to say the temperature in the room right now is 22 degrees Celsius up. Temperature doesn't have any direction associated with it, but a velocity does. And an important point about vectors is that they're independent of your choice of coordinates. Now, what I mean by that is actually rather subtle, and so I'll explain it later with some examples. So let's look at, say, water flowing in a channel, and these are vectors representing the velocity of the water at different locations, right? And so you see here, the water is going rather fast, and here it's rather slow, here it's going east, here it's going south. And if I label some of these, right, I can label a point A, and this vector VA is the velocity at A. Now notice, it's where the tail of the vector has been located in the diagram. So by VA, I mean that at this point, that's the velocity of the water. Somewhere out farther, like here, the velocity could very well be different. And now, compare writing down, say, the temperature at A. Let's say this is pretty hot water in a factory or something. It's 35 Celsius at point A. As opposed to if I'm going to write down the vector VA, it might be 2.5 meters per second east. And right there, that's the difference between a scalar and a vector. The scalar is just a number with units. The vector is a number with units and a direction. And now note something. Let's suppose VB was also 2.5 meters per second east. Now, VB is drawn at a different location here, but it has the same magnitude and the same direction. So those are equal, even though we've drawn them at different locations. You can slide a vector around. As long as you don't change its size or the direction it points, it stays the same vector. As opposed to this VC, let's say it had the same magnitude, 2.5 meters per second, but it was south. It is a different vector. It is not equal to A and B, even though its magnitude is the same. And just a note on notation. I'm using boldface here, but often I'll use a vector symbol. And depending on what you're working in, if you're handwriting, you should use a vector symbol, but if you're doing something in a word processor, say, getting a vector symbol on it is hard, so you do bold. So the way I've been writing these vectors so far is what's called magnitude direction notation, where you first write the magnitude and then you write the direction. And usually we enclose them in parentheses. So, for example, if I have this vector A, and let's say it's a displacement vector, and let's say it is 4 meters long, so that's its magnitude, and it's pointing in this direction, you need to be able to specify directions as precisely as possible. So let's say this angle here defines the direction of A. Then we could write it as 20 meters, 20 degrees below the positive x-axis. Now that might be confusing. You might be saying, but it's above the x-axis. What do you mean 20 degrees below the positive x-axis? Remember that we're talking not about a location here, but a direction. This A may be drawn above the x-axis, but remember, we can slide it around and that doesn't change what it is. But the direction it's pointing is 20 degrees below the direction that the x-axis points in, and so that's what we mean here. There's a convention that we call the direction of the x-axis 0 degrees, and then measure angles from it with counterclockwise angles being positive. So we could adopt that convention and just write this 4 meters, negative 20 degrees. Now, just look at a different sort of situation. Here's an airplane flying, and let's say it's flying in this direction. Okay, and here's a compass. We could write this as 110 meters per second, 55 degrees west of north, or we could write that 35 degrees north of west. Or if you know about compass bearings, that's bearing 305 degrees. It's 305 degrees around from due north. If we adopt axes, then we could use this convention. And notice if I put my x-axis along east, then this is pointing 145 degrees from the x-axis. But remember, I could choose to define my axes in a different way from that. So now we come to this subtle point that vectors don't depend on your choice of coordinates. And here's what I mean. Here's you and your friend Sam again. Remember Sam from a few lectures ago? And you're on one of these railway handcarts, and you're going east at 5 meters per second. So anyone would agree your velocity vector is 5 meters per second east. But you too may decide to define your axes differently. You each define a forward axis and an up axis. And having done that, you might describe the velocities this way: 5 meters per second forward for one of you and 5 meters per second backward for the other. So you disagree in how to write the vector down. But here's the thing. The vector itself doesn't depend on the coordinates. It is 5 meters per second east. If you and your friend both point in the direction of the vector, you're both going to point east. So you agree on the direction. You agree that it's 5 meters per second. But the way you express that is dependent on your choice of coordinates.